Hello everyone, today we are presenting our applied big data engineering mini project Smart City Traffic and Congestion System. This project demonstrates an end-to-end real-time big data pipeline using Kafka architecture approach. These are the team members of our project. Let's move on to the objectives. Actually, main goal of our project to build a complete real-time data engineering pipeline. We used Apache Kafka for data ingestion, Apache Spark structure streaming for streaming processing, PostgreSQL for storage, Apache Airflow for orchestration, and Docker Compose to manage the environment. The system continuously analyzes traffic condition and helps to identify congestion hotspot and peak traffic hours. We selected the Smart City Traffic Congestion System. Our scenario has 4 junction sensors simulated live traffic data like A, B, C, and D junctions. Each sensor sends JSON message every second containing sensor ID, timestamp, vehicle count, and average vehicle speed. The main requirement was to detect critical congestion when the average speed falls below 10 km per hour. When I move on to the architecture overview, first Python produces script simulate traffic sensor and generate streaming data. Then the data is sent into Apache Kafka topic. Spark structure streaming consumes the Kafka data and performs real-time processing using 5-minute tumbling windows. The process result and alerts are stored in a PostgreSQL. Finally, Apache Airflow runs scheduled nightly jobs to generate historical reports and peak traffic analytics. Now I will briefly explain why we select these technologies. Apache Kafka was chosen because it provides high throughput and fault tolerance real-time ingestions. Apache Spark Stream was used to event time processing and window-based analytics. PostgreSQL was selected as the storage layer because it is simple, reliable, and integrate easily with Spark. Apache Airflow handles orchestration and automates every nightly batch job. Docker Compose helps to us deploy and manage all services consistently. When I talk about real-time processing logic, actually real-time processing layer Spark continuously consumes traffic event from Kafka. The system groups event into 5 minutes tumbling windows and calculates total vehicle counts, average speed, and congestion index. Whenever the average speed drops below 10 km per hour, and system immediately trigger a congestion alert. These alerts are stored in a PostgreSQL and also published into separate Kafka topic called critical traffic. When I talk about event times and processing time, one important concept is streaming system is handling event time and processing time. Event time represents the actual timestamp when the traffic event occurred. Processing time is the time Spark received and processing the event. We use event time windowing because it provides more accurate analytic event when message arrive late. To handle delay efficiently, we implement watermarks in Spark structure stream.
Now we will demonstrate our smart city traffic and congestion system. Here we use a Lambda Kafka style streaming architecture. The flow is sensors, Kafka, Spark streaming, PostgreSQL, Airflow reports. First, we started all infrastructure services required for the pipeline using Docker Compose. As you can see, Kafka, Zookeeper, PostgreSQL, Airflow Scheduler, and Airflow Web Server are all running successfully. Now we can see all services are running successfully. Here, Kafka is running on port 9092, PostgreSQL runs on port 5432, and Airflow Web UI runs on port 8080. Then we verified whether all services started successfully. If any service failed during startup, we can inspect logs using Docker Compose logs. We created two topics: traffic events for incoming sensor data and critical traffic for congestion alerts. Now the Python producer simulates real-time traffic sensors from 4 Colombo junctions, junction A, B, C, and D. Every second, the producer sends JSON traffic events into Kafka containing vehicle count and average speed. When the average speed becomes very low, the system simulates heavy congestion conditions that are critical events.
After running the streaming traffic.python file, this Spark job will be started. You can see in the DAC file, and the Spark job will read messages from Kafka, process them in 5-minute windows, write aggregates to PostgreSQL, write alerts when speed is less than 10 km per hour. You can see this is the record from PostgreSQL. At first we have get traffic events, 10 events, and critical traffic events we limited it to 5. And in PostgreSQL we have fetched data from traffic events as well as critical events. They are fetched successfully. And then we can go to again the generate nightly report. After finding night peak hour and play button clicked, then we can click on the DAC graph view to see execution as this. And you can see here night peak hour graph execution. Actually, we have to wait for the task to complete, which is green check mark. We can see still the status is running. Then we can see the status is success. And the peak traffic relevant date CSV file has been generated in reports, Airflow reports. You can see the details here, sensor ID, peak hour, as well as the vehicle count. Then we can generate peak traffic relevant date comparison PNGs by giving this code to the terminal, and the images were generated. This is traffic value comparison across junctions, as well as this is the traffic volume versus time of day peak hours analysis.